We've searched the globe to find the world's toughest tools, from a 22-ton hammer to steel shears slicing through a derelict building. 6 monsters that dig and slice their way into the toughest substances on Earth. They are the Earth Beasts. In the US state of California, workers need to dispose of a major problem. Cars. Every year, Americans dump 10 million of them, enough to circle the globe twice. To stop all that rubbish from getting into landfills, one tool is transforming cars into flattened cubes of recyclable steel, the car crusher. This 13-metre wide monster crushes everything from the smallest car to the largest pickup into a 3-foot thick pancake of obliterated steel. Each vehicle is dealt a devastating 136-ton smash, the weight of 5 Sherman tanks.
It's strong enough, anything we throw at it, it's going to be flat.
Squashed to oblivion.
Not many people understand what happens to their car after they're done with it. You leave the car at the dealership, it disappears. But what happens is it comes to a facility like this.
Operator Bill's job today is to crush 200 vehicles. To meet the deadline, Bill will push the crusher to its limit and crush 2 at a time. The first 2 cars are fed to the machine. Though they were built to withstand high-speed crashes makes no difference to the crusher. A mere 12 seconds later, the cars emerge as compacted slabs, less than 25% of their original size, ready to be recycled into new steel. The engine driving the beast is only 152 horsepower, the size of a small family car. What gives the car crusher so much power is leverage and hydraulics. Combining the simple technology of a metal vise with the power of a hydraulic press, engineers were able to boost the 152 horses, enabling the crusher to munch down with over 900 kilos of crushing force per square centimetre. Slowed down, we see the car fail at its highest stress point, in this case the steel frame around the window. As the crusher applies pressure, the metal bends at the corner, exploding the glass outwards. To further demonstrate the mechanism of crushing, we put a drinks can into a household vise. When pressure is applied, the can yields at its highest stress point, surprisingly, the outside edge of its cylinder. Whereas a water balloon has no weak point. When a crushing force is applied, it fails uniformly. The power of the crusher enables Bill to mow through 25 cars per hour. He's well on his way to reaching the day's quota of 200 crushed cars. But suddenly, the crusher falters. One double stack of cars won't give in. Any delay could cause Bill to miss his deadline. To flatten the tough steel, Bill rocks the crushing plate back and forth. The plate shifts position from the front of the cars to the back of the cars. This causes the pressure load to change from an evenly distributed force to a more concentrated point force. This weakens the overall structure of the cars.
The rocker feature is awesome. It just gets them as compact as you can possibly get for shipping. It's just the only way to go.
Rocking the plate back and forth means the cars finally succumb to the power of the car crusher. Bill gets back on track and drags in more cars. He reaches his goal, 200 cars crushed in just 8 hours. The compacted wrecks will be shipped to the steel mills around the US and then melted down. And while it disposes of millions of junk cars each year, this car crusher isn't the only beast that annihilates vehicles. Nearly 5,000 kilometres away, a New Jersey tool is turning compacted cars into bite-sized chunks of scrap metal. Meet the car shredder. 6 stories tall and over 300 tons, the shredder makes mincemeat of every component on a car, including the solid steel engine. This also gets chewed up and spat out as steel mulch, ready for refining.
Once it gets to the machine, that's it. I mean, it's pretty much goodbye, Charlie.
Today, the shredder crew has a big job: destroy 2,400 cars and ship them to the steel mill. They know that to hit their target, the flow of cars to the shredder must be constant.
We want to run the operation as efficiently as possible. So it's in our best interest to keep feeding the mill or the shredder with as much material as possible. Get the material in, get it shredded, get it out.
2 giant cranes armed with grappling hooks have one task: just feed cars to the shredder. Mario operates the shredder as the cranes drop the first victims onto the tool's feed roll. This conveyor belt pushes each car towards the shredder's feed roll. Once it bites down, it's all over for the helpless vehicle.
Once it hits the feed rolls, we get about 4 to 5 cars per minute, which will be an average of 12 to 15 seconds per car that goes into the shredder.
Shredding the cars are 20 544 kilo hammers. Once the car is fed into the chamber, the hammers carry out the execution. Made of indestructible manganese steel alloy, these hammers rotate at 450 revolutions per minute, banging on the vehicle at the speed of over 280 kilometers per hour. This constant assault shears and compresses the material until it's small enough to pass through the shredder's sizing grates.
It's a wonderful experience being in control of a 9,000 horsepower motor of a mega shredder. It's just a fun, exciting experience.
When the hammers finish their work, the car emerges as small shards of steel. Halfway through the day, the guys are feeling confident. The car shredder has torn through almost 1,200 cars. They're right on target. But something big just got dropped onto the shredder's conveyor belt, a 12-metre school bus. The shredder's feeder system has stuck against the 12-ton piece of junk. Mario and his crew cannot afford any delay. In need of a helping hand, the crane operator moves in and grapples the bus, dropping it right at the mouth of the beast. Now it's time to shred. But the old bus still puts up a fight and the car shredder is jammed. Mario fights back and throws the feed roller into reverse. This clears the jam and the shredder tries again. But the old bus jams the tool once more. The crew is getting concerned and Mario can't afford to miss the 2,400 car quota. Finally, the shredder swallows the stubborn vehicle. This school bus won't be doing the school run again anytime soon.
I love my job. I get to come to work and destroy things. Since I was a kid, I like to destroy things, so I'm in a perfect career.
Mario then sets about shredding through the remaining cars and makes the day's quota.
It's extremely important to have a ready supply of steel. We're trying to help process those obsolete materials so they can be made into tomorrow's products.
Thanks to the car shredder, the junked cars in the US will become the next generation of steel products. As the crusher and shredder continue their vehicular destruction, another tool in the US is slicing through indestructible buildings. Condemned and abandoned buildings are a wasteland of concrete and steel. One building in the US city of Kansas was strong enough to survive severe tornadoes. But after 50 years of constant abuse, it's time to bring it down. and one of the world's toughest tools is on hand to do the job: the steel shears. Attached to a hydraulic excavator, the steel shears themselves weigh nearly 12,000 kilos. The jaw opens over 1 metre wide and extends to over 10 metres. They will snap shut and cut just about anything. And its bite? 2 tungsten steel cutter blades containing 4 separate cutting surfaces. But the sharpest teeth in the world would be useless without a force to back them up. This devastating power comes from its large bore piston, which converts 380 bar of hydraulic pressure into a formidable shearing force.
The shear that we're using today has 2,300 tons of force at the throat.
That's over 2 million kilos of force, 1,200 times the biting force of a great white shark. And a 6-metre steel girder is chewed up and spat out in just 5 minutes.
Nothing really stops the shears, it just keeps on cutting.
Today, the demolition crew needs to tear down 780 square metres of steel, concrete and wood by the end of their shift. But for this job, they can't just smash and bash. They've got to separate out the steel from the other materials. That valuable resource needs to be taken to the mills across the US.
We started by tearing the interior out to get rid of the wood, some of the sheetrock, that kind of thing. We separate the tin from the steel and push the concrete to the side.
And once the steel is separated, the steel shears must slice it all up into small chunks that the steel mills can use. Dividing and cutting up materials costs precious time, but it's worth it for the guys on the job.
Foundries seem to want smaller cuts, so the more cuts you make, the smaller the pieces, the more money they pay for it.
Time for the massive jaws to tuck in. Every hour, nearly 100 square metres of material must be cut up and removed.
The mobile shear is the most powerful scissors you can use.
And these industrial scissors are based on those from a life-saving job. Portable hydraulic power shears were introduced in the late 1970s to free motorists trapped inside wrecked cars. They were quickly nicknamed the Jaws of Life. Since hydraulic shears worked so well on lightweight metal, engineers upgraded the technology to cut heavy metal.
Leave the small tools behind because we've got the steel shear.
Mounted on the crawler-tracked hydraulic excavator, the steel shears have no boundaries.
Basically, it can walk over about anything we have on site here. Nothing gets in its way.
And the fully articulated shears handle all sorts of surprises that just happen to be lying around this abandoned site. Like a lead safe built to withstand earthquakes, explosions, and office colleagues trying to steal your sandwiches. An oxygen canister, an office filing cabinet, and of course, steel girders.
Our plan here is to cut the beams into 3-foot sections so that they can be loaded into a truck and recycled.
Brian positions the shears to make measured cuts, but the girder proves to be a tough adversary. That's because a beam like this can take a shot from the most powerful handgun in the world. A .50 caliber Smith & Wesson revolver. It doesn't even make a dent.
These are very, very large I-beams that we're cutting today, so we have to cut into one half, flip it over, and then cut through the second half.
The steel shears bite hard, and eventually the girder is cut into 2.
Without the steel shears, we would probably have to have a workforce of 30 people out here with cutting torches to get done what we're getting done with one steel shear.
By late in the afternoon, the crew has torn up nearly 740 square metres of rubble. The steel surrounding the site has been sliced and divided up, But they've put off the more dangerous work, and now it's time to get it done. These girders are still supporting the main part of the building. The shears must pull them free and then cut them up.
The steel beams are what is really holding everything together. When we're actually doing the demolition, we just pull one leg out, several feet of the mall will fall at one time.
Brian, the operator, knows that a mistake could bring the derelict building down on top of him. He must align the shears perfectly with the girder and then pull with constant pressure. But he's got another reason to be nervous.
That's the first time I'd done that. I hadn't even watched these guys do it. It just was new to me.
Steel beams that connect to support the structure are under tension. The tension is part of the design. It helps steel support many times its weight, so yanking on one of these girders guarantees collapse. Doing it the wrong way can result in injury or even death. To avoid a catastrophic collapse, safe cuts are marked so the shears can demolish the building safely. Brian carefully positions the steel shears and makes his move. Brian did the job safely as the debris falls around him. Taking a second look, it is clear that this building is no match for these steel shears.
You just don't want to sit there. You want to be backing out at the same time so the building don't fall on your boom.
Brian has got no time to relax as he has to take down the last section of the building to meet the day's quota. To safely demolish a derelict building whilst preserving the valuable steel inside takes one of the toughest tools in the world. The steel shears. The US state of Texas consumes more electricity than any other in the country, using coal as its main power source. But local coal in Mount Pleasant is buried under thousands of cubic meters of earth, called overburden. To extract it, Texans have called on the two largest excavation tools on Earth, the bucket wheel excavator and cross pit spreader. The bucket wheel excavator attacks the Earth first, doing the work of over 40,000 shovel-wielding men.
It's a mega machine, it's a big machine. How big? Big.
Attached to the 12-metre diameter wheel are 16 colossal buckets in constant motion. Their job is to shovel out the overburden by the truckload.
One scoop of rotation, I can fill a whole dump truck with it.
And what the bucket wheel excavator shovels up, the cross pit spreader spits out. This monstrous machine is the grandest of dirt chutes, weighing nearly 12,000 tonnes and standing 75 metres high.
You're looking at a machine that's 24 stories high, the size of 4 football fields, that weighs about 3 space shuttles fully loaded at the launch pad.
Constructing these two giants took 3 years and $35 million. Together, they use so much power that starting them simultaneously could cause blackouts.
They all run off of 25,000 volts. Comes from the power plant, and basically we have an extension cord that's plugged from the substation right into all the equipment.
Today, the bucket wheel excavator and the cross pit spreader are working at the Monticello mine, a 166-hectare open pit coal mine. The two tools must tear out 127,000 cubic metres of overburden so miners can access the 5,400 tonnes of coal beneath. Operator James G gets the bucket wheel excavator ready to dig in.
I've been operating the bucket wheel spreader for 10 years. It's one of the biggest ones in the United States, probably the world. I just enjoy running.
Running this earth-crushing predator takes years of experience just to program the computer for each dig. With his computer ready, James and the bucket wheel start scooping. Led by its 30-centimetre long teeth, the first bucket yields 2 cubic metres of dirt. For most, digging 127,000 cubic metres of overburden in a day is an impossibility. But the wheel's 16 buckets work in unison, ripping out over 34 cubic metres of dirt in every rotation. Driven by its 608 horsepower engine, the machine busts out 11,000 tons of dirt per hour, the same amount of rubbish the 12 million people of New York City produce daily.
The bucket wheel excavator is an amazing machine because without this machine, we couldn't dig as deep as we're digging.
By midday, the bucket wheel is halfway to its goal, excavating 127,000 cubic metres to reach the coal seam. But digging is only part of the equation. Each bucketful of overburden has to go somewhere. The cross-pit spreader picks up where the bucket wheel excavator left off, transferring the dirt to the opposite end of the mine pit. The dirt's chosen method of transportation is a conveyor belt nearly half a kilometre long. The result, a mountain range of dirt, metres high.
Dirt that's picked up by the bucket wheel takes approximately 1 minute to go through that whole system, and then it's shot out at the end.
Under operator Randy Green's supervision, the cross-pit spreader's mighty engine powers the overburden up the 240-metre boom arm at a speedy 27 kilometres per hour and launches it out the end at a distance of 9 metres.
This is truly an amazing machine that we got working here.
As impressive as the two tools are, they're only as good as the operators that run them.
The operator in the bucket wheel, the operator in the cross-pit spreader really have to sync up together so that the dirt from the bucket wheel gets transferred correctly to the cross-pit.
James and Randy both know that when moving mountains of dirt, the timing between each machine must be perfect. So far, the tools are in sync, and 85,000 cubic metres of earth have been cleared away from the coal. But suddenly, the bucket wheel and cross-pit spreader encounter their enemy, rocks. Most of the time, rocks are not an issue, but the bucket wheel has hit a particularly rocky patch of overburden. If the rocks are not dealt with, they will misalign the cross-pit spreader's conveyor system and shut down the operation.
Rocks are bad. They can cause a lot of damage into the system.
To stay on schedule, Randy issues an order to his partner.
You have to watch them real careful. If we get a belt misalignment, I can't produce, and if I'm down, he can't produce.
James makes the adjustment and keeps digging. Thanks to quick action, the problem is solved with no delays or damage. But Randy notices another potential problem. At the end of the spreader's boom arm, a mountain of dirt is growing. If Randy doesn't move the boom soon, the cross-pit spreader could get backed up. Luckily, the tool has a defence: dirt sniffers.
If the dirt gets too close to the boom, a siren will go off.
To move the spreader away from the dirt, Randy calls on some of the largest crawler treads in the world. Originally developed for transporting NASA's space shuttles to launch position, these 3-metre-tall crawlers loom over the men walking next to them. They have the ability to move the spreader in any direction at a steady 3 kilometres per hour. Not bad, considering the cross-pit spreader weighs 1.2 million kilos. The crawler moves away from the mountain of dirt and begins creating a new one.
The way it runs, it's just amazing how everything coincides with each other and makes it comes to one.
By the end of the day, the buried coal seam is finally exposed. 2 million kilos of dirt have been dug out. Loaders attack the exposed coal and haul it off to power plants. The bucket wheel excavator and cross-pit spreader, a Texan two-step that keeps the state powered and shining bright. As the miners begin attacking the unearthed coal seam, 3,200 kilometres west, a 180-ton hammer is reinforcing the planet by beating it senseless. Earthquakes strike without notice, destroying roads and bridges. To help eliminate future disasters, highways are built with deeper foundations. One tool in the US is doing it bigger and better: the diesel hammer.
Impact hammers are mean machines. They drive the foundation pile down to where we need them. These bridges could not be built without it.
Over 7 metres tall and weighing more than a jumbo jet, the diesel hammer pounds road foundation piles into the earth.
In a word that's used a little too often these days, it's awesome. This is one of the largest diesel hammers that is produced.
Its 22-ton ram slams down at a rate of 25 blows per minute. When it strikes, the results are explosive.
The force on these hammers is incredible. You want to talk about foot-pounds. These puppies put out 450,000 foot-pounds of energy on that thing.
The incredible power of the hammer is similar to that of a nail gun. Even when facing solid steel, the nail gun is a powerful weapon, exploding through the obstacle. When slowed down, the nail's impact causes the surrounding steel to shear away. The nail is shot out with so much force that the steel barely slows it down. In fact, the nail ricochets off the ground below the steel and bounces back into frame. When the diesel hammer strikes, the soil surrounding each pile has no choice but to give way, and the hammer doesn't take long to push them 45 metres deep, the equivalent of driving a 15-storey building straight into the ground. Today, the diesel hammer is in California, the heart of earthquake country. The goal? To pound in stronger support piles to carry the I-880 motorway. The foreman, Ron Stanville, knows the gravity of the task at hand. 200,000 drivers a day depend on the highway's safety.
If we don't do the foundation work underneath these bridges, they'll never hold up in an earthquake and thousands of people will die.
Ready to start pounding, Ron gives the go-ahead to the driving force behind the diesel hammer. Dennis Brand and his 226-ton Link-Belt 718 crane.
I pretty much control it. I lift it up. The only thing I don't do is light it off.
Dennis moves the hammer over the first steel pile. The positioning must be perfect. If the hammer and pile are not in line, the force of the blows could weaken the pile or drive it into the ground at an angle, compromising its load-bearing capabilities. Crew members direct Dennis from the ground as he guides the diesel hammer with the crane.
My flagman will tell me whether to boom up, boom down. They signal me in.
The hammer is set down on the pile. Dennis's reckoning is dead on. Now it's up to Ron to unleash the power.
These hammers are so strong and so powerful that there's nothing that we can't drive.
All its power and efficiency comes from one thing: continuous controlled explosions from the hammer's two-stroke diesel engine. As the hammer's ram drops, diesel fuel is discharged onto the surface of the impact block. When the ram strikes the block, the fuel ignites, driving the pile into the ground. This first explosion is the catalyst for more violence. The hammer strike ignites fuel and compressed air in the engine's cylinder. This second explosion drives the pile deeper. The blow is so powerful that the 22-ton ram is kicked back into its original position from the incredible force. Gravity pulls the ram back down and the cycle repeats, pounding the pile deeper and deeper into the ground. To further demonstrate the explosive strength of this chemical reaction, we packed an oven, as you do, with a similar chemical. One bullet striking the oven ignites the chemical. Slowed down, we see over 600,000 joules of dynamic energy released and the oven is obliterated. The diesel hammer unleashes the same amount of power with every stroke, 30,000 times a day. To withstand the diesel hammer's constant abuse, the road foundation piles are incredibly tough.
These piles are 165 feet long, 12-foot diameter, 1.25 inches thick.
Abuse from the hammer is not the only thing these piles must withstand. Deeper soil has high load-bearing capability, but it's also extremely dense. This harder soil increases the strain on the piles as they're driven in, increasing the chances of misalignment. Halfway through the job, the guys are growing concerned. The blows from the hammer aren't yielding the desired results. The ground might be too hard for the piles. If they're misaligned in the ground, the men will have to start again. Luckily, the crew has a solution: PDAs, or pile driving analyzers, which is a state-of-the-art monitoring system.
So we're looking at monitoring the last part of the drive until we get the pile down to near its final position.
The crew installed sensors called accelerometers and strain transducers at 4 key points around the pile: north, south, east and west. These sensors measure the angle and energy of each blow and determine how the pile is coping under the stress. This data ensures that the piles are being driven in as efficiently and safely as possible.
We can see if the hammer is not properly seated on the pile, if it's giving blows that are not axially aligned with the pile, and if the steel is being overstressed as a result of that.
With the PDA installed, the hammer slams back down on the pile and the PDA transmits the crucial data to the receiver. The data shows that the pile's alignment isn't perfect, but it is correctable.
It could have been aligned a little better. It was showing a harder blow on one side than the other.
The crew readjusts the hammer to correct the alignment and pounds the final pile home.
Feels good. I got 28 years in the union, Local 34. I'm proud to do the work.
With the piles driven in place, they're ready to be reinforced with concrete and steel mesh, or rebar.
When you have a solid steel shell and a solid concrete core pile with a solid rebar cage in the middle of it, there's not much going to go wrong with that thing. So it can withstand some tremendous amounts of force.
Protecting highways against earthquakes is essential, and the diesel hammer is the tool for the job. Modern society depends on coal for electricity, but tapping into some supplies is dangerous for traditional mining crews. The Prairie Eagle mine in Illinois, the US, has a way of extracting black gold previously left in the dark. The High Wall Miner. Standing 9 metres tall, 16 metres long and 10 metres wide, the monstrous machine dominates its landscape. At the business end is the cutter head module. This 3 metre wide rotating drum has a set of razor-sharp carbon steel teeth called bits. Their job, to chew through mountains.
Right now we're using the toughest graded bit we can get.
These jaws attack the high wall with a staggering 136,000 kilos of muscle and won't stop until they find their prize, coal.
These teeth penetrate into the seam and basically just shear it away from the piece next to it.
That much power would require 20,000 men. The High Wall Miner requires only 4.
It takes 4 guys to run this machine and they can get a lot of work accomplished. It's a great machine.
But today's task is a tough one, even for the High Wall Miner. The crew must bore 290 metres into this previously inaccessible rock face and then dig out 1,500 tonnes of coal in 10 hours.
We can mine about 120 feet in an hour's time.
To succeed, the miner will have to take 188 tonnes of coal out of the mountain every hour. By hand, such a pace is impossible. The average man can muster 75 kilos of digging force, but for a very short period of time. But mechanised mining tools are changing the industry.
To see the technology that we've had today from 20 years ago, 30 years ago, you know, it's real impressive.
The miner attacks any mountain head-on and keeps its operators out of harm's way.
The high wall in a surface operation is one of the more dangerous spots to be at.
Boring directly into the side of a mountain wall increases the risk of collapse. If it happens, the results could be deadly. But the High Wall Miner is making danger a thing of the past, thanks to one important innovation: push beams. Push beams are 6-metre extensions that can be attached to the miner's cutter head. This allows the tool to bore deeper into the mine. Each 5,000 kilo extension is attached using the High Wall Miner's built-in crane system. Once in place, a power head pushes the cutter deeper inside the mine.
If we can move back as far away as we need to, maintain a safe distance from the wall.
The miner can handle 50 push beams at a time, giving it a maximum reach of 304 metres. Here, men underground is a thing of the past. As the cutter head moves deeper, the push beams serve another purpose, extracting the coal. As the coal is torn out of the mountain, it's brought back to the miners by the push beam's internal conveyor belts.
Inside each beam, there is two 18-inch augers, one turning the opposite direction of each other that extracts the coal, that moves the coal from the front of the machine to the back of the machine.
Once the coal gets back to the miner, a stacker belt lifts the coal to the loading zone. The coal is then transferred off-site and delivered around the world. Back at the job, the high wall miner is 250 metres into the mountain, well on its way to reaching the goal of 1,509 tonnes of coal. But suddenly the amperage gauges spike sharply. The cause? The cutter head has struck solid rock.
On the cutter head amp gauges, if it starts spiking up a little over 100, you know you're hitting hard rock.
If hard rock gets mixed into the load, it will compromise the purity of the coal, but the high wall miner has a defence system. Resistance gauges mounted on the cutter head tell the operator where to mine for coal and how to avoid the rock. Once the miner detects the path of the coal, the operator can control the direction of the cutter head by using the miner's hydraulic system. Thanks to flexible joints on the cutter head and push beams, the miner can follow pitches and rolls in the coal seam, even from 300 metres away. Utilising this technology leaves the unwanted rock behind and gives the power plants the good stuff. At the end of the day, over 1,450 tonnes of coal has been mined. Mission accomplished.
We can mine 2,500 tons of coal in 12 hours time with 4 to 5 people. This machine is pretty phenomenal.
The high wall miner is really one incredible machine. It's amazing to sit and watch it and see what it's capable of doing.
The high wall miner mines coal safer, faster and more efficiently than ever before and leaves all other methods in the dust. While miners prepare the fresh coal for delivery, in the US state of Florida, one tool stands between the state's largest freshwater lake and a natural disaster. Florida's Lake Okeechobee is the second largest freshwater lake in the US, but the old levee that protects Florida from massive flooding cannot withstand a direct hit from a hurricane.
If the dike did fail, it could possibly flood all of South Florida.
It must be rebuilt. There is only one tool for this urgent task, the trench cutting and remixing deep wall machine, better known as the TRD saw. The TRD is a triple threat. It cuts an extremely deep trench, mixes cement and sets a levee wall. Rigged to a 90-ton modified crawler crane, it stands 10 metres tall and has a 475 horsepower engine that would probably make a Porsche jealous. The TRD tears up the terrain with an oversized chainsaw. Each carbon steel tooth is 60 centimetres wide and 15 thick. Once it slices the ground, the cement mixer dumps 5,300 litres of concrete an hour to make the earth stronger. Only a handful exist in the US. Today, this rare tool is set to carve a massive wedge into the earth surrounding the lake.
To make this dike stronger and to make it safe for hurricanes and floods, it required an underground wall to be constructed through the dike.
An elite crew has been building a 1.9 kilometre length of the 230 kilometre levee.
We have done approximately 5,000 feet of that. We have another 1,500 feet or so to go.
Today, they'll dig out and pour a 21-metre stretch of the most high-tech levee in America. Traditionally, levees were low-tech, a simple wall made of mud and rock, but water can quickly soak and weaken these materials. Eventually, all natural levees will be breached. It's just a matter of time. Concrete and other man-made materials are the only way to make a levee that can withstand Florida's punishing storms. The TRD was born to plant these synthetic materials where man cannot.
It is a solid wall. It's designed to keep the dike from failing.
The crew starts at 3 metres, the length of the cutter, but quickly needs to get to 21 metres. The TRD crew finds another gear and digs deeper. When the picture is slowed down, we see each tooth on the blade has to be built tough enough to withstand its travel through solid rock and wet cement. A tooth on a TRD is constructed of ultra-high carbon steel, enabling it to withstand a 22-metre plunge into and out of the ground. Carbon-infused steel is harder and stronger than standard steel, two qualities the TRD demands.
Most of our work you never see. It's down in the ground. If we've been there, it's better than what it was when we got there.
As the crew reaches 9 metres, they have only one concern on their mind: keep vertical. If the TRD falls out of the vertical, the cutting chain can be destroyed. For now, the saw is set in its cutting motion. Each 60-centimetre wide tooth tears at the soil much like a chainsaw. To further demonstrate the TRD saw's action, we've immersed a chainsaw blade into a mixture of oil and water. The water represents the dirt, the oil is the cement. Slowed down, it's easy to understand how the saw works. As each tooth rotates, it cuts through the rock and pulls the cement. This mixes the two materials into concrete, creating an instant wall. After a few hours, the TRD has cut through rock, sand and clay for 12 of the 21-metre target, but the TRD operator has spotted a problem. The optical surveyor's tool has indicated that the cutter box has fallen out of vertical alignment, a potentially disastrous issue.
Just like a saw cutting through wood, if you get the blade out of verticality, you can get bound up. The same thing can happen with the cutter post. So we have to make sure that for the safety of the machine and the durability of the machine, we have to make sure we keep a vertical wall.
The laser guides the machine. It shoots 2 crosshairs on 2 targets in the front and the back of the machine. And as long as the laser is hitting both crosshairs, you know that it's in line with your wall.
Sometimes if the cutter post is drifting a little bit out of vertical, he makes adjustments, raises and lowers it to get the verticality back in place.
We do have a good system of checks and balances to make sure that we are building quality wall.
Once the massive cutter is vertical again, the TRD can continue. The crew's target is accomplished, a 21-metre long, 21-metre deep section in one day. Once the entire 230-kilometre wall is completed, over 5 million cubic yards of soilcrete will have been used.
That's a pretty impressive machine. There's not many machines that can dig and mix a wall 70 feet deep in a dike.
Which is why the TRD is one of the world's toughest tools.